happy to welcome our today's speaker, Professor Rahul Roy from ISI Delhi. And before starting with the talk, I would like to request you all to keep your audio on mute. However, if you want to ask any question, please do it over the chat box and wait for a signal from uh, from me. So the before unmuting your audio. And so, uh, can we start, Rahul?
Sure.
Yeah, thank you. Welcome.
Okay, so the title of my talk is Voter and Majority Dynamics with Biased and Stubborn Agents. And this is joint work with Arpan Mukhopadhyay and Ravi Mazumdar. And Arpan was actually we were jointly supervised by Ravi and me at University of Waterloo. Arpan Mukhopadhyay right now has a job at the University of Warwick, and Ravi is still at University of Waterloo. Oops. Okay. This problem actually started many years ago when Onish, Ontor, and I worked on a certain problem which was there in the advances in applied probability, and then this is a continuation in some sense of that. Although I haven't given all the references, as I told you, this has appeared in the Journal of Statistical Physics last year, and this is open access because Ravi Mazumdar has money to pay for it, and so you can find the references in that paper. So the social learning literature studies how social agents, human beings for example, interacting with under simple rules, learn the true utilities of their choices, opinions, or technologies over time. In this context, the two central questions we study are, can social agents learn or adopt the better technology or opinion through simple rules of interactions? And if so, how fast? And the second is, what are the effects of the presence of stubborn agents who have fixed opinions on the dynamics of opinion diffusion? So the way I want to think of it is that, so there are these two operating systems, Linux and Microsoft. Okay, and people who are, there are very stubborn Linux users, like in the audience, I can think of Onish and Deepayan for whereas there are others like me who can vacillate between anything and use whatever is convenient. So the stubborn agents would be people who are stubborn about using Linux or stubborn about using Microsoft Word, Microsoft OpenOffice or whatever. Okay. So what we do is we consider a setting where the choices available to each agent are binary and are represented by 0 or 1. These are referred as the opinions of the agents. And the interactions amongst the agents are modeled using two simple rules, the voter rule and the majority rule. Right. Although I'm just talking in terms of social science and everything, this is mathematically a question. What we are studying is an interacting particle system. As you'll soon see, for those of you who are knowledgeable about interacting particle systems, you can see that it's actually an interacting particle system, a la Spitzer and others. Okay. In the voter rule, an agent randomly samples one of its neighbors at an instant when it decides to update its opinion. The updating agent then adopts the opinion of the sampled neighbor. Okay. Remember, the sampled neighbor can have its own opinion. In that case, there is really no change in the opinion. And this simple rule captures the tendency of an individual to mimic other individuals in the society. In the majority rule, instead of sampling a single agent, an updating agent samples 2K neighbors. I want to keep it 2K because as you'll see soon, 2K neighbors, and adopts the opinion of the majority of the sampled neighbors, including itself. Because it includes itself, it becomes 2K plus 1, so there's always a majority. There's no tie. And this rule captures the tendency of the individuals to conform with the majority opinion in their local neighborhoods. And this is, in some sense, when k equals 1, what Anish, Antor, and I studied was how the majority rule, when individuals are placed on a single line, how that evolves. And in that sense, this is a continuation of some work which Anish, Antor, and I did nearly 15 years ago. Mathematically, what we are doing is that we have a network of n social agents. Opinion of each agent is assumed to be a binary random variable taking values in the set 0 or 1. Initially, every agent adopts one of the two opinions in an IID fashion. And each agent considers updating its opinion at points of an independent unit rate Poisson point process associated with itself. Again, for the mathematical physicists in this audience, this is just a Poisson clock associated with each individual. A Poisson clock is a clock which rings after a Poisson time, and according to a Poisson point process, when it rings, the agent updates its opinion. And because the Poisson point process is a continuous time process, therefore, we all know that the two distinct Poisson clocks will never ring at the same time with probability 1. Okay. So at a point of the Poisson point process, or in other words, when the Poisson clock rings for that person, he or she then updates its opinion or retains its past opinion. So this is what I have to explain now, retains its past opinion, and that I will do shortly. Okay. So we assume that an agent with opinion I, so opinion I can be 0 or 1, or Microsoft or Linux, updates its opinion at a point of a unit rate Poisson point process associated with itself with probability Qi. When I mean update, it means that it samples one of the other n-1 individuals and gets the opinion of this individual, and either updates means if the opinion is 0 and my opinion is 1, then I update means I change to 0 with probability Qi. And with probability Pi, I don't change, even if the opinion of the sampled person goes against me. Whereas if, that's why I use the word updates rather than change, whereas if I sample somebody whose opinion agrees with mine, then of course I don't change my opinion at all. And we want to make the agents biased towards opinion 1. So what we assume is that Q0 is bigger than Q1. Q0, remember, is the updating probability when your opinion is 0, and Q1 is the updating probability when your opinion is 1. So this implies that an agent with opinion 1 updates its opinion less frequently than an agent with opinion 0. In the voter rule, an updating agent samples an agent uniformly at random from the n agents. I'm saying with replacement, although there's only one being sampled, but the with replacement is for the majority rule. That's what I want. The reason because we will finally look at the asymptotics in n. So whether we are looking at it with replacement or without, it really doesn't matter. The results would would be the same. In the majority rule, an updating agent samples 2k agents, where k is bigger than or equal to 1, uniformly at random, again with replacement, and adopts the opinion of the majority of the 2k plus 1 agents, including itself. And although I'm just sampling for the entire population available to me of n agents, all our results can actually be extended to the case when instead of n, we have when n is the total population and we sample from a fraction of this n. So from a random group of size big O of n, if we sample, the results do not change. However, for simplicity, we only focus on the case when the sampling occurs from the whole population. Okay. So I'll tell you the results and then we'll have some discussion later. Mm. We first consider the voter model with biased agents. So biased agents means, if you remember, Q0, the probability that I update my opinion when my opinion is 0 is bigger than Q1. In other words, the probability when I update my opinion when my opinion is 1. So that's the biased voter model. In this case, clearly the network reaches consensus in a finite time with probability 1. And that's because there's a very simple analogy with random walk in this case. And our interest is to find out the probability with which consensus is achieved on the preferred opinion 1. This is referred to as the exit probability of the network. And we also characterize the average time to reach consensus. The case when it is unbiased, in other words, when Q1 equals Q0 equals 1, that's the standard voter model with unbiased agents. And it is known that for this voter model with unbiased agents, the probability with which consensus is reached on a particular opinion is simply equal to the initial fraction alpha of agents having that opinion. In other words, if you remember, I said that the n agents choose their opinion in an IID fashion. So if the probability is alpha of choosing 1, then the initial fraction of ones, the expected number would be alpha, and that's where the consensus with probability alpha, the consensus would be 1. Okay. And the expected time to reach consensus for large n is approximately n times h alpha, where h alpha is this entropic term minus of alpha log n log of alpha plus 1 minus alpha log of 1 minus alpha. So it's n times this entropic term. Okay. So this is for the voter model with unbiased agent. This is a very well known. These are very well known results, and I think originally it was started by Ted Cox and others, and there are these references in our paper, but I'm not going to give those references here. So now we proceed to characterize these quantities for the voter model with biased agents. So let x and t denote the number of agents with opinion 1 at time t. Clearly, x and t is a continuous time Markov process on the state space 0 up to n. And 0 and n are the absorbing states. Okay. The transition rates from state k are given by from k to k plus 1, it goes with probability. See, k is the number of ones. So to go from k to k plus 1, the individual who is updating must have opinion 0, and then it has to sample 1 from the k who have opinion 1, sorry, n minus k who have opinion 1, and k is the total number of people who have opinion 0. So it's k times q0 times n minus k by n. That is the actual way of writing this, which turns out to be this quantity. Similarly, from going from k to k minus 1, so that means the person who is updating must have opinion 1, and he or she changes his or her opinion to 0, and the number of people with opinion 1 is k. So q1 times k is the way of number of ways of choosing one of these ones, and n minus k over n is the probability of sampling somebody whose opinion is 0. So this qij denotes the rate of transition from state I to state j. The embedded discrete time Markov chain, which I call x tilde n for xn, is a one-dimensional random walk, as I told you, with jump probability p, which is q0 over q0 plus q1, p to the right, and 1 minus p to the left. And as we all know, the way to study the hitting probabilities of 0 or n is through go through q over p, which is r, and in our case q is bigger than p is bigger than q, So R is strictly less than 1, and R bar, which is 1 over R. And this is the way, one way to study it. And through that study, what we'll easily get, we can just quote the results from random walk, is that if Tk denotes the first hitting time of state K, in other words, Tk is the infimum of T such that xnt is bigger than or equal to K, we are interested in the asymptotic behavior of the quantities pi and alpha, which is the probability starting with an alpha proportion of individuals at time 0 being 1. What is the probability of hitting n before hitting 0? That's pi n alpha. And T n alpha is the expected time of hitting one of the boundary points. Whereas I said Px or Ex denotes the probability measure and expectation conditioned on the event that at time 0 there are X individuals of opinion 1. Or if you want, you can think of this small x as the binomial, the Bernoulli probability of being 1. Our first theorem characterizes the mean time Tn alpha to reach the consensus state starting from alpha fraction of agents having opinion 1. Mathematically, this means that the initial distribution of the opinions were IID Bernoulli, with alpha being the probability of having an opinion 1. And for our result is that if alpha is between 0 and 1, we have that Tn alpha is, well, this theta of log n just means that it is big O of log n asymptotically almost surely. That is the mathematical the symbol theta, which is used in probability. So it is big O of log n, but asymptotically as n goes to infinity. So this theorem shows that the mean consensus time in the biased voter model is logarithmic in the network size. And this is in contrast to the voter model with unbiased agents, where the mean consensus time is linear in the network size. Thus, with biased agents, the network reaches consensus exponentially faster. We also now study the measure-valued process, small x of n, which is, remember, x of n at t is the number of people with opinion 1 at time t. So x of n by n, which is nothing but the proportion of people with opinion 1 at any time t. Okay. So this describes the evolution of the proportion of agents with opinion 1. We show that the following convergence takes place. Namely, if xn at time 0 is binomial n alpha, then we have that this proportion, small x of n, converges in distribution to this process x as n goes to infinity, where, well, this is weak convergence or convergence distribution because we're talking about a random variable. And x dot is a deterministic process whose initial condition x of 0 is alpha and is governed by the following differential equation, that x dot t equals q0 minus q1 times x of t times 1 minus x of t. So this is so for those with some knowledge of mathematical physics, what we have really described is the mean field limit of this process. Excuse me. So we'll use this mean field limit to obtain various results. So according to above result, the mean field limit, for large n, the process xn dot is well approximated by the deterministic process x dot, which, as I told you, is called the mean field limit of the system. And using the mean field limit, we can approximate the mean consensus time Tn alpha by the time x dot takes to reach the state 1 minus 1 over n. So instead of looking at 0 or 1, we just look at 1 minus 1 over n, starting from alpha. And then what we have is this result, that for the process x dot, which is the mean field limit, we have that x of t goes to 1 as t goes to infinity for any x0, starting from any x0 in 0 and 1. And if T epsilon alpha denotes the time required by the process x dot to reach epsilon in 0 and 1, starting from x0 equal to alpha, then T epsilon alpha is given by this function, 1 over q0 minus q1. Remember, q0 was bigger than q1, so this is a positive quantity. Logarithm of epsilon over 1 minus epsilon minus logarithm of alpha over 1 minus alpha. In particular, for epsilon equal to 1 minus 1 over n, we have that this is T of 1 minus 1 over n alpha is this quantity, which, as you can see, is of the order of log n. Okay. The process x dot does not reach 1 in a finite time, even though the process xn does reach 1 in the finite time. And the reason is because the mean field limit is really looking at the asymptotics in n. Whereas for a fixed n, it is just a regular Markov process, and therefore it will get absorbed at 0 or 1 with probability 1 and a finite time. However, it is reasonable to assume that Tn alpha is closely approximated by T of 1 minus n alpha. Tn alpha, remember, is the average time of absorption. Okay. And such approximation of the absorption time of absorbing Markov chain using its corresponding mean field limit is quite common in the probabilistic and the mathematical physics literature nowadays, because in some sense the mean field limit gives us the asymptotics of the system, or again the finite volume limit, as they say. However, except for a few special cases, there is no really rigorous theory justifying such approximations. So, although this mean field limit is used a lot in mathematics nowadays, there's really no rigorous theory which justifies these approximations. Okay, coming back to the unbiased voter model, where that means when q0 equal to q1 equal to 1, the mean field limit is simply xt equal to alpha for all t bigger than or equal to 0. And hence, in this case, the mean consensus time cannot be approximated with the mean field limit. So, as opposed to the biased case where we got the mean field limit here, which was non-trivial, and therefore we can use it for various things. For the unbiased case, you just get xt is identically equal to alpha for all t bigger than or equal to 0, and hence this really doesn't give us anything. Okay, for the majority rule model, recall that the majority rule model is the model where an individual samples 2k out of the n, the population of size n. It samples 2k, where 2k, of course, has to be strictly less than n. And then the agent who samples changes his or her opinion to that of the majority. Okay. Again, there is a retention term in the sense that with certain probability, the agent does not change his or her opinion, and with a certain probability, he changes his opinion. Okay. In this case, the transition rates or the jump rates of xn from state n to n plus 1, remember xn is the number of ones at any time t. So from going from n to n plus 1, again, the individual who is sampling must have opinion 0 and has to move to n plus 1. And that you can see is given by this term. I'm not elaborating on this. It's basically a binomial term, binomial 2k with probability small n over n, small n being the probability of a person. Sorry, this is the probability at any given time t of an individual being 1. So binomial 2k with this probability, and because there are 2k plus 1, so this binomial has to take value bigger than k plus 1 for the individual who's sampling to change his or her opinion from 0 to 1. And similarly, going from an opinion of 1 to 0, in which case the total number of agents with opinion 1 change from n to n minus 1. That happens with if an individual who samples has opinion 1 and samples somebody whose opinion is 0. And that is given by this quantity. So here, remember, so the difference between this is that it's n over, this is the probability of an individual being 1 at that time, and this is the probability of an individual being 0 at that time. Because we are sampling from the number of people from the 0 should be more than k plus 1 for me to change my opinion. So if x tilde n, as usual, denotes the embedded Markov chain, the discrete time Markov chain corresponding to xn, then the jump probabilities for the discrete time Markov chain are given by the probability of going from n to n plus 1, which is the probability of 1 minus, which is 1 minus probability of going from n to n minus 1, is this quantity. And if you recall the binomial expressions, I can write this as gk small n over n divided by gk small n over n plus r, where r, remember, is q1 over q0, and gkx is given by this binomial ratio. This is a very interesting ratio, and well, I mean, we really spent 6 months trying to understand this quantity. So let me just elaborate on this. This is 1 over x, where x is the probability of success of a binomial random variable, and the binomial there are 2k comma x, and the probability that it's bigger than or equal to k plus 1, and below it's 1 over 1 minus x, where 1 minus x is the probability of this binomial random variable, and the probability that this is bigger than or equal to k plus 1. And it really took us quite some effort, as I told you, 6 months, but then the proof was simple to prove this lemma. But anyway, I'll come back to this. So with probability 1, xn gets absorbed in one of the states 0 and n in finite time. We are interested in the probability of absorption in state n and the average time till absorption, just like in the questions which we asked in the voter model case. And the lemma, the key lemma, is this result, that the function gk, which is this quantity, so x, remember, is the probability of success of a binomial in the numerator and the probability of failure in the denominator. So this probability being between 0 and 1, we only look at strictly between 0 and 1, otherwise the entire thing becomes trivial. So what we show is that this gk as a function from 0, 1 to 0, infinity, it's well, it is non-negative because all the terms here are non-negative. Is strictly increasing and is therefore also 1 to 1. Okay. And using that, we actually characterize the exit probability, and we get a surprising phase transition here. So let pi n denote the probability that the process xn, remember, is the number of individuals out of those n who have opinion 1. So the pi n, the probability that the process gets absorbed in state n, starting from the state small n. Then we have that pi n, this probability is given by this ratio, whereas you can see this gk's again come in important. And if we define pi n alpha as the probability that the process gets absorbed in state n when the initial proportion of people with opinion 1 is alpha, then we get this, that this pi n alpha goes to 1 as n goes to infinity if alpha is bigger than a certain quantity beta, and pi n alpha goes to 0 as n goes to infinity if alpha is less than beta, where beta is exactly the gk inverse of r. K, remember, is the 2k was the number of people who are being sampled by the individual. And both these convergence are exponentially fast in n. So this is what I wanted to explain by saying that there is a phase transition in this system. So depending on if the initial population alpha is bigger than beta, then we go to 1, otherwise it goes to 0. Okay. And so as I said earlier, that we have a phase transition of the exit probability at beta for all values of k. Okay. Of course, when I say for all values of k, beta depends on k through this function g inverse of kr. Okay. This implies that even though the agents are biased towards the preferred opinion, consensus may not be obtained on the preferred opinion if the initial fraction of the agents having the preferred opinion is below the threshold beta. And this is in contrast with the voter model where consensus is obtained on the preferred opinion irrespective of the initial state. Okay, and this is actually where Anish Antor and I were writing the paper, our paper. Antor wanted to call this that the underdogs get an advantage in the sense that though the agents are biased towards the preferred opinion, consensus may not be obtained on the preferred opinion if the initial fraction of the agents having that opinion is below the threshold beta. Mm-hmm. And because beta is, as I told you, is just GK inverse of R, so we can obtain beta through just by a Newton-Raphson method by solving this equation, GK beta equals R. We note that for the unbiased majority rule model, we have R equal to 1 because Q0 equal to Q1. And then in that case, beta, which is GK inverse of 1, is half. Thus, the known results for the majority rule model with unbiased agents are recovered from this. And we also characterize the mean time of consensus. But the mean time of consensus is, if you're not at the critical point beta, it is asymptotically theta of log n. Or in other words, it's big O of log n, asymptotically almost surely in n. The above theorem shows that in both the regimes, alpha less than beta or alpha bigger than beta, the mean consensus time is logarithmic in the network size. So it really goes exponentially fast to the consensus. And to prove this theorem, we need branching processes and a very special kind of branching process. And it's a bit non-trivial, but you can see it in our paper. And for those who are interested, I can tell you later about this. And we also need the monotonicity, of the GK function, GK of x, which I stated as a lemma. Okay. Here also we can derive the mean field limit corresponding to the empirical distribution, small x of n, which is capital Xn over n. Okay. And using the transition rates, which I had talked about earlier, we know that we can see that if the initial distribution is binomial n alpha, then this the empirical process Xn converges weakly to a process X, which is given by the following differential equation, ordinary differential equation, x dot t equals q0 of xt 1 minus xt. Remember, just this part, which I'm highlighting, this was exactly the part which came in the for the mean field limit for the voters model. For the majority rule, we have something extra, and that is given by the second half, which is, I'll tell you what HK is. HK is just connected to GK. HK of XT times GK of XT minus R. So this is the extra term in the mean field limit. And HKX is nothing but the probability that, there's no probability. It's 2K choose I, 1 minus X. So the binomial probability of this quantity, of the binomial random variable taking a value bigger than k plus 1 when the probability of success is x. Okay. Again, by definition, hx is bigger than 0, and using lemma 4, we can show that the x dot has 3 equilibrium points at 0, 1, and beta. This is where the reason why beta comes in important in that in this theorem. In this theorem, this is the reason why beta comes in important, but this is the reason which we obtain this beta through a branching process, and we also obtain it again through this mean field limit. Okay. Yeah. So using the monotonicity of GK, which we established in lemma 4, and the non-negativity of HK, we have that the X dot T is bigger than 0 for XT bigger than beta and less than 0 for XT less than beta. This shows that the only stable equilibrium points of the mean field limit are at 0 and 1, and beta is an unstable equilibrium point. Now we move to the studying the majority rule model in the presence of stubborn agents. What do I mean by stubborn agents? So these are agents that never update their opinions. So if I like Linux and I'm an ardent fan of it, I will never move to any other Microsoft or Mac or anything. I'll just stick to my Linux operating system. And the other agents referred to as the non-stubborn agents are assumed to update their opinions at all points of the point process associated themselves, just like earlier. And we focus on the case where the updates occur according to the majority rule. The voter model with stubborn agents was studied before using coalescing random walk, and therefore we are not studying that. However, this method of using coalescing random walk, because the voter model really is can be equated to a random walk, and in this case with the stubborn thing, it just becomes a coalescing random walk. But we cannot really use this random walk understanding for the majority rule model. Instead, what we do is we use the mean field techniques to study the opinion dynamics under the majority rule model with stubborn agents. And I must say that we just have the mean field results. We really do not have a concrete way of understanding the Markov chain without this mean field, unless we go through this mean field limit. Okay. So we denote by gamma I the fraction of agents in a network who are stubborn and have opinion I at all times. So gamma 0 is the fraction who stick to the opinion 0, gamma 1 who stick to the opinion 1, and 1 minus the remaining is the proportion of non-stubborn agents who are willing to change his or her opinion. The presence of stubborn agents prevents the network from reaching a consensus state because there'll always be a proportion gamma 0 with opinion 0 and a proportion gamma 1 with opinion 1. As I said here. Furthermore, since each non-stubborn agent may interact with some stubborn agents at every update instant, it's always possible for the non-stubborn agent to change its opinion. We characterize the equilibrium fraction of non-stubborn agents having opinion 1 in the network for large N using mean field techniques. And for analytical tractability, we consider the case k equal to 1. In other words, we are just sampling 2 agents at every instant when we update. However, the similar results holds for larger values of k, but analytically it becomes really non-tractable. So let x and t denote the fraction of non-stubborn agents having opinion 1 at time t. So this is a fraction. So this is it's xn of dot is really an empirical process. It's a Markov process with possible jumps at the points of rate n times 1 minus gamma 0 minus gamma 1 Poisson process. The process xn dot jumps from the state x to the state x plus. Remember, I'm looking at a fraction, so I have to look at this fraction instead of 1. Earlier, I was looking at from n to n plus 1 because I was counting individuals. Now I'm just looking at the fraction. So it moves from x to this quantity when one of the non-stubborn agents having opinion 0 becomes active, and which happens with this rate, and samples 2 agents with opinion 1, because If I am opinion 0, for me to change, I have to sample two people, both of whose opinions are 1. Otherwise, I won't change. And the probability of sampling an opinion having opinion 1 from the entire network is exactly this quantity. Remember, X is the proportion of people who have opinion 1. And the total rate at which the process transits from state X to the state X plus this quantity is given by this. So this is the transition rate. And as you can see, there's a square term here. Okay. And that really comes from the fact that there are stubborn agents. Similarly, the rate of going from X to X minus something, so the proportion of ones decreasing, can also be obtained in this fashion. And as in the mean field theorem for the voter model or for the majority rule, we can show that the above transition rates converges weakly to the mean field limit, which is given by this expression. X dot t is 1 minus xt, and this is the number of non-stubborn people who can change their opinions. And this gamma 1 is the proportion of stubborn agents who do not change their opinion and stick to their opinion 1. Similarly, gamma 0. And so we get this as the mean field limit. And we want to understand this differential equation. So the equilibrium distribution pi n of the process xn for large n by the equilibrium, we can obtain this by from the equilibrium points of the mean field x dot. And from that differential equation, we see that x dot t is a cubic polynomial in xt. Hence, the process x can have at most 3 equilibrium points in 0 and 1. We first characterize the stability of these equilibrium points. The process x dot defined above has at least 1 equilibrium point in 0 and 1. Furthermore, the number of stable equilibrium points of x dot is either in 0 and 1 is either 2 or 1. And if there exists only 1 equilibrium point of x in 0 and 1, then the equilibrium point is globally stable, or it's an attractive equilibrium point. And in what we are going to do now, we are going to provide the conditions on gamma 0 and gamma 1 for which there exist multiple stable equilibrium points of the mean field x dot. Okay. So there exist 2 distinct stable equilibrium points of the mean field x in 0 and 1 if and only if this quantity gamma 0 minus gamma 1 squared plus 3 of 1 minus this quantity is bigger than 0. And if I take Z1 and Z2 to be these quantities, then if Z1 and if Z2, the product must be less than or equal to 0, where f of t is given by this function. If any one of these, if any one of the above conditions fails, then x has a unique globally stable equilibrium point. So for it to have 2 distinct stable equilibrium points, we need condition 1 and condition 3 for Z1 and Z2 given by this quantity. Hence, depending on the values of gamma 0 and gamma 1, in other words, the proportion of stubborn agents, there may exist multiple stable equilibrium points of the mean field x dot. However, for every finite n, the process xn has a unique stationary distribution mu n, because, of course, for the process xn is irreducible on a finite state space, and therefore it will have a unique stationary distribution. Okay. Any limit point of the probability measure mu n is a convex combination of the Dirac measures concentrated on the equilibrium points of x dot in 0 and 1. In particular, if there exists a unique equilibrium point R of x dot in 0 and 1, then mu n converges weakly to the measure which gives all mass at R, which is a Dirac measure concentrated at the point R. So now I want to end with some simulations. Remember, this work was done with two computer scientists, so they love to simulate. Of course, for me, if I need any simulation, I immediately run to the Pion. Okay. In this figure, what we plot is the equilibrium point of x dot when it is unique as a function of the fraction gamma 1 of agents having opinion 1 who are stubborn, keeping the fraction gamma naught of stubborn agents having opinion 0 fixed. So fraction of agents having opinion 1 with stubborn, who are stubborn is gamma 1. This is given here. And then I've given you the equilibrium point of the mean field when gamma 0 is 0.6, when it's 0.4, when it is 0.7, etc. So this is the majority rule with stubborn agents, and equilibrium point of x as a fraction of gamma 1 and gamma 0, where gamma 0, of course, is being fixed at 0.6 or 0.4 or 0.27. We choose the parameter values. So the parameter values which we chose was so that there exists a unique equilibrium point, and that came from our theorem in 0, 1. And such parameter settings can be obtained using, well, I call it a theorem, sorry, using the conditions of that theorem which I wrote earlier. We see that as gamma 1 increases in the range from 0 to 1 minus gamma 0, the equilibrium point shifts closer to 1. And this is expected since, just if you see, this gets closer to 1. Okay. And this is expected because the increasing the fraction of stubborn agents with opinion 1 just increases the probability with which a non-stubborn agent samples an agent with opinion 1 at an update instant. If there exists multiple equilibrium points of the process x dot, then this convergence implies that at the steady state, the process xn spends intervals near the region corresponding to one of the stable equilibriums of x dot. Then due to some rare events, it reaches via the unstable equilibrium to the other stable point. This fluctuation repeats itself, giving a unique kind of a stationary distribution. And this is, in physics, it's known as the metastability. And to demonstrate this, what we do is we take gamma 0 equal to gamma 1 equal to 0.2, n equal to 100, and from the theorem, we know that the mean field x has two stable points at 0.12 and 0.87. And what we are going to do is to draw the sample path of the process, the empirical process. And what we'll see is that it just changes back and forth between the two opinions, 0 or 1. Yeah, it changes really very dramatically. Okay. What would be interesting to study would be the amount of time, the distribution of the amount of time when it is, let's say, close to less than 0.2 or above 0.8. So, and that would be interesting to study, but we really have no way of studying that right now. Okay. To end this, what we are where we really worked on a complete graph of n agent in the sense that we were sampling from any one of my neighbors, n-1 neighbors. So it was a complete graph. And now if we change the network topology, and then we want to see what happens. So in particular, instead of the complete graph, what we look at is the connected d-regular graph. D-regular means that every vertex has exactly d neighbors. And in graph theory or random graphs, these are called graphs which have near optimal expansion properties. I don't want to get into that. But what we get for these numerically, this is completely simulation. What we get that for these d-regular graphs, they behave exactly like the complete graph. So what we are looking at in the simulation which we do, we look at 3 regular random graphs, and we observe that the mean consensus time is theta of log n when the agents are biased, as opposed to theta n when the agents are unbiased. And this is what we get. So this is the unbiased agents, which grows as n, and otherwise it grows as log n. And for the parameters are given here. In the next figure, the exit probability is observed to increase exponentially to 1 with the increase in alpha for the biased voter model that we already saw, and as opposed to the linear increase in the unbiased voter model. Hence, the observations are qualitatively different in the case of complete graphs. And well, we do the same thing for the 3 regular random graphs for the majority rule. And so this is given here. But this, by the way, this talk would be available. Tanvi can tell you where it will be available. So if you want more, you can see these simulations. I don't want to go through these simulations, but these were needed because our referee asked for these simulations. Okay, so with this, I'd like to end my talk, and I want to quote Ambrose Bierce. What is a talk? It's a transitive verb: to commit an indiscretion without temptation from an impulse without purpose. And this is an indiscretion without temptation because I actually asked Tanvi if I could give a talk. So it was really an indiscretion without temptation. And it came from an impulse without any purpose. Thank you.
Thanks, Rahul. In fact, it was my great pleasure that you asked, and we could hear your talk. So,
well, you've been
any
hearing
question?
at least once a year, no? I mean, I give talks at least once a year.
I'll be happy if we can hear you more.
No, that's too much. The Ambrose Bierce also has a definition of a person who is a bore. Bore is a person who talks when he should be listening. So, okay, so then you'd start calling me a bore.
Oh, by that time, then I'll let you know.
Okay.
Though that can be rude, but yeah. But that stage will never happen. So I think you need not worry about that. Any questions from the participants?
Questions, Sarkar.
This is Antar. May I?
Yeah, please.
Yeah, first of all, Rahul, thank you. It's a wonderful talk and a really good slides, very easy to understand. So what I wanted to ask you is that when you were showing about the deregular graphs, the simulations, so when you are doing the majority, are you still going to sample from everybody or only from the neighbors?
From the neighborhood, from the people with whom I'm connected.
Okay, so you are really looking into the network topology.
Right, right.
You also do for the more classical one, the Eros-Renyi type random graphs?
Well, we are not really doing it for an Eros-Renyi random graph. So therefore, in the earlier case, we were looking at a complete graph N, but in the Eros-Renyi random graph, if we are in the situation where there is a giant component, okay, then in that giant component, we can, and suppose it's the Eros-Renyi random graph also evolves over time so that the giant component at every time is different, because then we already have an order n neighbors, each one of us.
Right.
So in that case, all the results would go through. That's my feeling. We haven't really done any calculations, but because what you really need is an order n neighborhood for yourself.
Okay. Okay. All right. I would suggest that an interesting one would be to look into the above the connectivity threshold. So when your P is above log n by n,
right,
Eros-Renyi type model, that what it actually gives you, because then your neighborhood are not of the order n, but
Right.
of the order somewhere around log n, near about the connectivity threshold, not too much above the connectivity threshold.
Yeah, then
Of
it
course,
becomes an order n, the giant graph, the giant
Right.
component arrives.
Right.
Right. But at the criticality when everything is log n, then I don't know what we can
No,
get.
then it might be very, very difficult.
Right, right.
So the other thing, what is a little more detailed study is, so you showed us that there is this changes happen when there are more than one
Right. Equilibrium points.
right? Now, since you have done simulation, have you noticed that clusters are forming in some part of the network, and then all of a sudden they are changing all together, right?
Exactly. So that's exactly. Let me get the picture then, and tell you what we really want to study. So this is exactly what's happening, right? What is an interesting project, and to be honest, I have no idea what to do, is to look at the time spent. In some sense, it's a local time question. Time spent below the fraction point 2, which I mark here, or above the fraction point 8, let's say. Okay, and look at it as a function of alpha, the proportion, and instead of 0.2, I can say, okay, what is the time spent below alpha or above a beta?
Right.
That would be an interesting question, because that just tells you that, okay, there is this equilibrium point, you're getting attracted to it. Okay, but because you're a non-stubborn person, suddenly you have sampled a lot from the other group, and in which case you're actually pulling nearly all of yourself, all others up.
Right.
Okay, so that is that's what this graph shows, and therefore it's really a very interesting question to study the proportion below a fraction alpha, how much time you spend there, etc.
Right. Yeah. Thank you. Very interesting work.
Thanks.
Any other question? So if there are no more questions, let's unmute ourselves and thank Professor Rahul Roy for the nice talk.
Thank you, everybody.
Thank you.